Hi, based on the continuity lemma, I can now prove the law of rare events for you. In the previous video, we have seen that convergence of the generating functions implies convergence of the mass functions. As a corollary, I would like to first show you the Poisson approximation of binomials, and then we're going to extend those ideas to prove the law of rare events. Okay, so let's start with the Poisson approximation. Of binomials. And the setup will be the following. We are going to have a binomial random variable xn of parameters n and p. However, p is going to be a function of n. So the parameter p is a function of n. And we're going to assume, so we're going to say that this is such that as n goes to infinity, Pn will go to 0 in a way that the product n times Pn is going to converge to a positive real lambda, to some positive real parameter. Okay, so n goes to infinity, Pn goes to 0, the product converges to a positive real parameter, lambda. Notice that np is actually the expectation of my binomial, right? So this lambda is some kind of a mean value in the limit as n goes to infinity. So that's the setup, these are the assumptions, and then the statement is that then for every k integer, we have that the probability of xn equals k converges to a Poisson probability of that parameter lambda, namely lambda to the k over k factorial e to the minus lambda. That's the statement. One could also say that xn converges in distribution to the Poisson lambda random variable, to the Poisson lambda distribution. Okay, or if you want, binomial np with this Pn converges to Poisson lambda in distribution or weakly. Okay, and let's prove this. The proof is quite easy once we know the convergence of mass functions, because that's all that really happens. We look at the generating function of xn at s, in other words, the expectation of s to the xn, and you can look this up, or you can just remind yourself that we have a binomial. A binomial is the sum of n IID Bernoullis of parameter Pn. For the Bernoullis, we have xn equals to 0 with probability 1 minus Pn, and then it equals to 1. So that gives me an S with probability Pn. Okay, and we have n of these things because the binomial is the sum of n IID Bernoullis, and that means that we have an nth power for the generating function. And the good way to rearrange this is to collect the one, this one here, separately, and then see what else is next to this one. And what we find is the following. We have a, let's do it this way. We have s of Pn and minus 1 of Pn. And another thing I want to do is I want to add a factor n, which I'm also going to cancel. So I add in this factor n, which I'm also cancelling out. All this is raised to the nth power. And the reason I did that is that Pn times n converges to lambda. So that part goes to lambda. This part here goes to lambda by assumption. And if you have a convergent sequence in the numerator, and you divide it by n in this fraction and you raise it to the nth power, then you have a well-defined limit, a well-known limit, and that is just going to be e to the s minus 1 of lambda. Okay, so if you have a convergence sequence here, 1 plus the convergence sequence here divided by n to the nth power will just converge to the limit of this whole business, which is s minus 1 lambda raised to the exponential. Okay, and this is the generating function of Poisson lambda at s. So we have shown that the generating functions converge, and that implies, according to the continuity lemma for generating function, it implies that the mass functions also converge, so we do have the weak convergence. An example, let me show you a simple example. Suppose that there is a city, and the city has 500,000 citizens in a city. Let's assume that there are also 100 post offices. So let's assume that there are 100 post offices. There are 100 post offices. Okay, and let's assume that every person is going to the post office very rarely, maybe once a year. So let's assume that each person goes to the post office independently today with probability 1 over 365, so that means that on average a person goes once a year. And let's assume also that independently of everything they pick uniformly out of the 100 post offices. So pick one of the 100 post offices uniformly with equal chance and independently of everything else. And now what I'm after is the number of people who go to post office number 1. So post office number 1 will see a binomial number of people of parameter 500,000, and the probability of a particular person going to that post office is 1 over 365 for the particular day of a visit, and 1 over 100 for the particular post office to visit, because they are picked uniformly. And so that's a binomial random variable with a large n parameter and a rather small p parameter, and then you can just work out the details. You can just multiply these together, so the 500,000 and this probability, and this is going to be very close, according to the previous theorem, to a Poisson 13.7 distribution. So the number of people visiting that post office is approximately Poisson 13.7. That actually is going to be a very, very good fit under these assumptions. Okay, so this was pretty much known, and what I want to do next is generalize the thing to the actual law of rare events, because more than this is true, and generating functions will provide a nice tool to actually prove a more general version of this. So the actual law of rare events has again a couple of assumptions. So let x n k, where k goes between 1 and n, and then goes from 1 to infinity, so n at least 1, and k goes between 1 and n, be independent Bernoullis I do not assume that they are identically distributed. They are independent, but I don't need identical distribution. And I want to assume that the probability x and k is 1 is, well, that's just notation, it's p and k. Okay? That's the starting setup. Now, before I proceed with that, let me explain a little bit what this means, what we're doing here. So a triangular array means that when n is 1, then k is 1. So I have x1, 1 as a random variable. When n is 2, then I have k equals 1 and k equals 2. And when n is 3, then I have k equals 1 and k equals 2 and k equals 3, and so on and so on. And this is a setup which is also called a triangular array of random variables. Okay? And what we need to assume is that these random variables are independent. In particular, what's really important is that particular rows are independent. So going across rows are independent. So what we really need here is that the rows are independent. It's actually no problem if we have some dependence across the different rows. So if I take x1 one dependent of x2 one, that's perfectly fine. What I need is independence within one row. Okay. Another remark I want to make here is that if you have a Bernoulli random variable, then you could also think about the probability it's 1 as the mean of that Bernoulli. Bernoulli is 0 or 1, the probability it's 1 is equal to its mean. So assume that you have Bernoullis with mean P and K. Okay, now I have some assumptions on the P and K. So I need two assumptions. Suppose assumption 1 that across a row, if I fix n, so n is going to fix the row. Let me make that clear here. N equals to 1 is the first row, n equals to 2 is the second row, n equals to 3 is the third row. So fixing a row and looking at the largest of the P and K within that row. So K between 1 and n, the largest of the P and K has to go to 0 as n goes to infinity. Okay, so these probabilities must vanish even if I take the largest one within a row. As I go further down and down in this triangular array, the largest of the probabilities still goes to 0. That's my first assumption. So it's some kind of a uniformly small probability assumption. There is no single P and K that will take a lot of the mass within a row. So that's the first assumption, and I have a second assumption that the sum from 1 through n of the P and K converges to lambda as n goes to infinity. Okay, notice that this thing depends on n but not on k. So as n goes to infinity, it converges to lambda, and this lambda is a real number, not 0 and not infinity. So there is a positive finite limit of this sum. The statement is that then if you look at the sum from 1 through n of the x and k, this will converge in distribution to a Poisson random variable of this parameter lambda. Okay, so we have V convergence or in distribution convergence of the sum of the x and k's to Poisson lambda. And now again I want to explain a couple of things. The first thing I want to explain is that if you look at the sum of the Bernoullis, a Bernoulli is also an indicator. The sum of the indicators is just the number of events that occurs. So if you consider these Bernoullis as indicators of some events, then this is going to be the number of events, at least across a row, that occur. Okay, so the total number of events will converge to a Poisson lambda random variable. And what is lambda? Lambda is actually the expected number of events that occur. And why is that? Because these are 0, 1. So if I take an expectation of the sum, that's the sum of the expectations, and the expectation of x and k is exactly the P and K parameters. So I have the sum of those. So this thing is exactly the expectation of the sum of the x and k's, and that's assumed to go to lambda, and then the actual number will go to Poisson with that expectation. Poisson lambda has expectation lambda. Okay? So if you have uniformly small probability events, the expected number of them converges to lambda, then the distribution will converge to Poisson lambda. Okay, let me show you the proof of this statement. And in order to do the proof, well, first I switch colors, and I'm going to start with a little bit of analysis. We need a bit of analysis for that. I'm going to find out about log of 1 minus x, okay, because we'll need this. So let's start off with the following thing, and all through this proof my x variable will be a real number between 0 and 1/2. So take a real number between 0 and 1/2 and start looking at the sum of x to the n as n goes from 0 to infinity. This makes perfect sense because 1/2 is smaller than 1, so this is a geometric series, it's summable, everything is fine, and the answer is 1 over 1 minus x. So now if I do an integral of both sides with respect to x, then on the left hand side I find a sum. N goes from 0 to infinity, x to the n plus 1 over n plus 1, and that's because it's non-negative, and for non-negative sums it's okay to swap integration with infinite sums. And on the right hand side I'm going to have a minus log of 1 minus x and the constant, and that's because 1 over something integrates to log, and because of this minus sign I have the minus in front. Now plug in, for example, x equals to 0. X equals to 0 gives me 0 on the left hand side, it also gives me 0 on the right hand side for the log, and that concludes that this constant is 0 if one plugs in x equals to 0. And also a little bit renaming the summations. I'm going to introduce m equals to n plus 1 for a new summation variable, and that will tell me that a minus sum from 1 to infinity of x to the m over m is the same as log of 1 minus x. Okay, so that is going to be an important starting point. And you'll see in a second why. Well, the reason is that if I look at the generating function, if I want to look at the generating function of what I need, so what do I need? I need the sum of the x and k's, which are independent across this sum. So for different k values, these guys are independent, and they are Bernoullis of parameter p and k. So the generating function of the sum of k from 1 through n of the x and k, because of them being Bernoulli and because of them being independent across different k's, it is going to be so the generating function itself is going to be a product. K goes from 1 through n of the generating function of the x and k. The generating function of all this at s is the product of the generating functions at s. And what is the generating function for Bernoulli? It's going to be, so the Bernoulli could be 0 with parameter 1 with probability 1 minus p and k, and it could be 1 with probability p and k, and these generating functions are multiplied together for different k's. Okay, and that's my generating function. Let me write this in a slightly nicer form. So just a little bit of variation. What I want to see is a 1. If I have a product, I always like to see 1. And what I want to see next is a minus and a 1 minus s, p, and k. And clearly it's the same thing because I have a 1, I have a minus p and k, I have a plus s, p, and k. The reason I want to see it in this form is that I always like 1s in a product. And notice that p and k is small. P and k uniformly goes to 0 as n goes to infinity. The maximum among k is still going to 0. So p and k is small. And at this moment, what I want to do next is take a logarithm of this. So Actually, I want to call this whole business Pn of s. It's good to have a notation for that. So take a natural log of Pn of of s. It is going to be a sum. The product becomes a sum of the natural logs of 1 minus s p n k. Okay, and now comes the bound, which we concluded down here. Now comes the bound in blue. The bound in blue, I'm going to apply it in two directions. So let me turn back to blue a little bit. Okay, so blue said that log of 1 minus x, and notice that x is between 0 and 1/2 for this proof. So log of 1 minus x is equal to minus this sum, minus sum from 1 to infinity x to the m over m, and I'm going to apply two bounds on this. My first bound is going to be an upper bound. This thing is smaller than its first term. Actually, I'm going to, before I do that, I'm just going to separate the first term. So what is the first term? The first term is minus x to the first over 1, and then I have this sum from 2. And now what I'm going to say is that this is smaller than minus x. For every x between 0 and 1/2, I have some positive terms here. They are subtracted, so this whole business is smaller than minus x. But I can also separate the second term in the following way. So I can also continue here that log of 1 minus x, maybe let's do it this way. Log of 1 minus x, I can also write this as minus x, minus, I can factor out x squared from this sum, and then say that we have, well, let's do it this way. M equals to 2 to infinity, x to the m minus 2 over m. And this thing, so over m is at least 2. Over m make this thing smaller than if I forget about m. Dividing by m make this thing smaller than if I forget about m. Okay? And if this thing is smaller, it is subtracted, and everything else is positive, it is subtracted, so the whole thing is going to be bigger than minus x squared, the sum from 2 to infinity of x to the m minus 2 without the over m. If I forget about dividing by m, then I make this term larger. Apologies. Then I make this term larger, and the whole thing is going to be smaller. Okay? Which is something I can calculate. Minus x, and then I have minus x squared. This is again a geometric sum, just starting with x to the first power, x to the 0th power, going up to infinity. X is between 0 and 1/2, so it's a geometric sum, easy to calculate. And x is less than 1/2, 1 minus x is larger than 1/2, divide with it, the whole thing is smaller than 2x squared, so because of subtracting, the inequality goes this way. It is going to be minus larger than, the whole thing is larger than minus x minus 2x squared. Okay, again, x is smaller than 1/2, 1 minus x is larger than 1/2, this whole fraction is smaller than 2, it's subtracted, so the whole thing is larger than if I replace the fraction by 2. Okay, so these are the two estimates which I'm going to further use to actually bound P and S from both sides. So now I can bound P and S from both sides. And this tells me that log of P and S is on one hand smaller than the sum. This is going to be my x inside all of the terms in the sum. So I'm going to apply an upper bound of minus x, and so I'm going to put here a minus 1 minus s p and k, and I'm also going to give a lower bound. This is going to be my lower bound here, and that's going to give me a sum of minus 1 minus s p and k for the x term. And I also have, let's do it this way, and I also have a minus 2. I can separate this sum, and the square of whatever I had inside, so that's 1 minus s square p and k square. All of this is my lower bound. Okay. So, for the upper bound, things are easy because I know where this thing converges to. This thing converges to a minus 1 minus s times the sum of the p and k goes to, by assumption, the sum of the p and k goes to lambda. So this thing converges to minus 1 minus s times lambda. And the same thing happens here. This thing converges to, again, minus 1 minus s times lambda as n goes to infinity. But I need to do something with that error term. This is going to be an error term. Clearly I can factor out the minus 2. I have a minus 2. I can factor out the 1 minus s square. S is fixed between 0 and 1, so there's just some number there. What I need to look at is the sum of the p and k squared, okay, which is the sum of probabilities, so it's non-negative. It's actually, let's make it non-negative, but I want to give you an upper bound on this, and here is what I'm going to do. It's the sum of p times p. Now one of those p's I'm going to replace by something, and the other of those p's I'm going to keep. So I keep one of those p's, and I replace the other one by the largest of them. I replace the other p and k by the largest of them across the k's. So I'm going to put here the max of k hat between 1 and n, p n and k hat. So I'm looking at the largest of the p's in that sum. That's the maximum. I'm going to pull that out. That makes my whole business larger than before. If I replace one of these p's by the maximum of them, that makes it larger. And then after I've done that, I can factor out this maximum, and I'm left with this guy here. And now I can say that this goes to lambda by assumption. The sum of the p and k's goes to lambda. However, the maximum of the p and k's goes to 0. That's my other assumption. So this maximum, as n goes to infinity, this thing goes to 0 as n goes to infinity. And therefore this whole limit goes to 0 as n goes to infinity, because one part of it goes to 0, the other part goes to lambda, the product goes to 0. So that shows me that all of this vanishes in the limit. That orange business shows me that all of the second term vanishes in the limit. Okay, so I have log of the generating function. It's sandwiched between two terms. One term that goes to minus 1 minus s lambda, and the other term that also goes to minus 1 minus s lambda. So what I conclude from here is that the generating function for the sum p of s, sandwiched between two terms, each of which goes to, I had a log, each of which goes to 1 minus s lambda with a minus sign in front, right? The sandwich, both sides of the sandwich goes to minus 1 minus s lambda. So I conclude that the log of Pn itself has to converge there. This is a negative number. It's absolutely fine. It's log is continuous at negative reals. I mean the range of log. So log is continuous when the range is negative real, and therefore Pns has to converge as n goes to infinity to exponential of minus 1 minus s lambda, or if you want, exponential of lambda s minus 1. However, this is exactly the Poisson generating function. Okay, so this is the generating function of Poisson lambda at s, and what I showed is that the generating function of the sum, which I called Pns, converges to the generating function of Poisson. So that means that the sum itself, k goes from 1 through n, x and k, converges in distribution to Poisson lambda. And we are done with the proof. That's exactly what we stated. Okay, so that's the law of rare events. And let me just show you the example we had before with the post office. So before we had 500,000 people in a city, and let's assume that these 500,000 people are of the following mix. So we have, say, 100,000 children, we have, say, 100,000 students who are not children anymore, and say we have 200,000 in employment, and say we have, and then say not students, and say we have 100,000 at home, adults at home. And so let's assume that each of these groups go a different number of times to the post office. So the probability of visiting a post office is going to be 0 for children, for on a day. Let's put here a day, because children don't go to the post office, so let's assume that. For students it's 1/2 over 365, because let's assume that a student visits a post office on average 1/2 times a year. Let's assume that somebody in employment will visit the post office once a year on average, so on each day it's 1 over 365. And those who stay at home, let's suppose that they visit the post office, well, just a number, let's put it 2.5, just to make the numbers a bit nicer. So let's assume that they visit the post office 2.5 times a year on average. And then if we're looking at the number of visits, number of visitors or number of customers in post office number 1 today, then this is going to be the sum of 100,000 visits of mean 0, so those don't count of course, 100,000 Bernoullis of mean 1/2 165 times 1 over 100, 200,000 Bernoullis of mean 1 times 365 is 1 over 100, and 100,000 Bernoullis of mean 5/2 times 1 over 365 is 1 over 100. Okay, so we have, so this is going to be the sum, say from 1 to 100,000 of x and k, where, okay, let me just write it out first. So say 100,001 to 300,000 of x and k again, and then a sum from 300,001 to yes, to 500. What am I doing here? This should be 200,000. This is 2 and this is 400,000 of x and k, and then 400,000. Everybody gets the pattern, right? It's just, I just want to separate these groups. So these are the children, these are the students, these are the employed people, and then these are the stay-at-home people. Okay, and those x and k's are assumed to be independent Bernoullis, but the mean, the parameter p and k, is different for each of them. Okay, so p and k in this range is 0 for children. P and k for the next 100,000 people, the students, is 1/2 over 365 and 1 over 100. So this is the probability of going to the post office on a given day, and this is the probability of going to that particular post office, number 1. For the third group, it's going to be 1 over 365 over 1 over 100,000. And for the last group, it's going to be 5/2 over 365, 1 over 100. Okay? And the theorem says that this sum, even though it's not IID, but it's still independent Bernoulli summed up, the probabilities, each of these probabilities is very small, the numbers are very large, so this will be very close to a Poisson parameter, sorry, a Poisson random variable of parameters all added up, so 365 and 100, and then we have not enough space. Let me do it down here. So Poisson, okay, all added up 365 times 100 down here, and so we have 100,000 of 1/2 for the students. We have 200,000 of 1 for the employed people, and we have another 100,000 of 5/2 for the stay-at-home people. Okay, and you just add all these up and you get an answer, right? So you get a Poisson of parameter 1/2 plus 5/2, that's 3, and you have a 4 here and the 5, so it's 5 times 100,000, which actually is the same as before. So it's the same as in the previous example with a homogeneous Poisson thing, which is 13.7. Okay, so this example shows you that even if your Bernoullis are not IID but still independent, you still have this Poisson approximation.